Hello and welcome to Earth Science, Lecture 1. Before we begin with this course, I'd just like to make a few notes. First of all, if you're a student of mine, you'll see that in these videos I often will link to other videos that I would like you to watch. In an effort to avoid copyright claims, I just link these in the YouTube description of every video. So anytime that I come to a slide where I recommend going to watch a video, just pause this video and go take a look at that one. So it is required as part of the course. It aids in your understanding of these materials that I present to you. Also, at the end of each lecture, you will find a bunch of quick check questions, as I call them. So there are a series of multiple choice questions. The answers are given. The goal of these is for you to just read the question, pause the video as you contemplate the answer, and once you think you have an answer, simply go to the next slide and the answer will be revealed. So you'll often be pausing the video in order for this to work. And last but not least, I just want to mention that I do now have a dog, so occasionally my dog is a little goofy. You might hear some sounds in the background. So if that does ever occur, I do apologize for that. So without further ado, let us begin. So what exactly is Earth science? We need to start from somewhere. Well, Earth science is the name for all of the sciences that collectively seek to understand the Earth and its neighbors in space. So this, of course, will include things like geology, oceanography, and meteorology. But believe it or not, this also does include some astronomy as well, as we look beyond our own Earth. So let's break down each one. What exactly is geology? Geology literally means the study of the Earth. Geology is traditionally divided into two broad areas, both physical and historical. The aim of historical geology is to understand the origin of the Earth and the development of the planet through its 4.6 billion year history. It strives to establish an orderly chronological arrangement of the multitude of physical and biological changes that have occurred in the geological past. Physical geology examines the materials composing Earth and seeks to understand that the many processes that operate beneath the surface and upon the surface. Earth is a dynamic and ever-changing planet. Internal forces create earthquakes, they build mountains, and they even produce volcanic structures. At the surface, external processes break rock apart and sculpt a broad array of landforms. The erosional effects of water, wind, and ice result in a great diversity of landscapes. Because rocks and minerals form in response to Earth's internal and external processes, their interpretation is basic to an understanding of our own planet. So, Earth science, as we mentioned, is also oceanography. Earth is often called the blue planet, and such a term relates to the fact that more than 70% of the Earth's surface is covered by the global ocean. If we are to understand the Earth, then we must learn about its oceans in what we know is oceanography. Oceanography integrates chemistry, physics, geology, and biology all into one. So it includes the study of the composition and movements of seawater, as well as coastal processes, seafloor topography, and as well as marine life. Now, a disclaimer before going into this course, we will barely touch on oceanography in our course, just as we aim to focus on other subject areas. Earth science is also meteorology. Acted on by the combined effects of Earth's motions and energy from the sun, the formless and invisible atmosphere reacts by producing an infinite variety of weather, which in turn creates a basic pattern of global climates. Meteorology is the study of the atmosphere and the processes that produce both weather and climate. Like oceanography, meteorology involves the application of many other sciences in an integrated study of the thin layer of air that surrounds Earth. Note we say thin, it's relatively thin compared to the size of the Earth, but we'll touch on that much later in our course. Well, as I mentioned, Earth science is also astronomy. An understanding of Earth requires that we relate our planet to the larger universe. Because Earth is related to all other objects in space, the science of astronomy, that is, the study of the universe, is very useful in probing the origins of our own environment. Because we are so closely acquainted with the planet on which we live, it is easy for us to forget that the Earth is just a tiny object in a very vast universe. Indeed, Earth is subject to the same physical laws that govern the many other objects populating the great expanses of space. Thus, to understand explanations of our planet's origin, it is useful to learn something about our other members of the solar system. Moreover, it is helpful to view the solar system as a part of the great assemblage of stars that comprise our galaxy, which in turn is but one of many galaxies. So by the end of this course, we will expand into the universe as a whole. Some physical phenomena are relatively easy for us to imagine, such as the size and duration of an afternoon thunderstorm or the dimension of a sand dune. Other phenomena, however, are so vast or so small that they are difficult to imagine. The number of stars and distances in our galaxies and beyond, or the internal arrangements of atoms in a mineral crystal are examples of such phenomena. Some of the events that we study occur in fractions of a second. Lightning is an example. Other processes extend over spans of tens to hundreds or even millions of years. The lofty Himalaya mountains began forming nearly 50 million years ago, and they continue to develop today, for example. When viewed in the context of Earth's 4.6 billion year history, an event that occurred 100 million years ago would be characterized as relatively recent to a geologist, and a rock sample that has been dated at 10 million years might be called young, even though you think about 10 million years on a human timescale, and that seems like a ridiculous amount of time. So, for example, how long is 4.6 billion years? Well, if you were to begin counting at the rate of one number per second, and you did this for 24 hours a day, 7 days a week, and never stopped, it would take about 2 lifetimes, or about 150 years, for you to count to 4.6 billion. So the Earth is quite old. Our entire solar system formed from a vast rotating cloud of gas and dust that we call the solar nebula. The model of this formation is known as the nebular hypothesis. We will touch on this a lot more later in the course. Each part of the nebula exerted a gravitational attraction on other parts, which tended to make the nebula contract. The nebula then heated, began to spin, and flatten into a disk. It is from this disk that the planets began to form and that we were able to come from. So you can see this here. It shows just a big solar nebula, which is just a cloud of gas and dust. It starts to collapse due to gravity. It starts to spin and heat up. And then we see our planet start to develop out of all the material as it cools down and gives us our current solar system today. Well, bringing it back home, we have to consider some of the Earth's spheres. So our environment is highly integrated and is not dominated by just rock, water, or air alone. It is instead characterized by the continuous interactions as air comes into contact with rock, rock with water, and water with air. Moreover, the biosphere, which is the totality of life forms on our planet, extends into each of these 3 physical realms and is equally an integral part of the planet. Thus, Earth can be thought of as consisting of 4 major spheres: the hydrosphere, the atmosphere, the geosphere, and the biosphere. So let's take a look at each one of these. Starting off with the hydrosphere, water, more than anything else, makes Earth unique. The hydrosphere is a dynamic mass of water that is continually on the move, evaporating from the oceans to the atmosphere, precipitating to the land, and running back to the oceans once more. The global ocean is certainly the most prominent feature of the hydrosphere, blanketing nearly 71% of Earth's surface to an average depth of about 12,500 feet. It accounts for about 97% of Earth's water. However, the hydrosphere also includes the fresh water found in streams, lakes, glaciers, as well as that found underground in groundwater. Although these later sources constitute just a tiny fraction of the total, they are much more important than their meager percentages indicate. In addition to providing the fresh water that is so vital to life on land, streams, glaciers, and groundwater, are responsible for sculpting and creating many of our planet's varied landforms. So here I just give 2 figures. The first shows the breakup of the content of our hydrosphere. So almost 97% of all water on Earth exists in our oceans. But some of that, which is fresh water, exists in our glaciers, groundwater, and streams. And then here I show an example of the water cycle, which we will touch on much more when we begin our discussion on the atmosphere. All right, so one of the other Earth's spheres is the atmosphere. Earth is surrounded by a life-giving gaseous envelope that we call the atmosphere. When we watch a high-flying jet plane cross the sky, it seems that the atmosphere extends upward for a great distance. However, when compared to the thickness or radius of the solid Earth, which is about 4,000 miles, the atmosphere is actually a very shallow layer. One half of the atmosphere lies below an altitude of just 3.5 miles, and 90% occurs within just 10 miles of the Earth's surface. To give you a really interesting example, the average apple is about 225 millimeters around, and its skin is 3 millimeters thick. If we compare the Earth and its atmosphere to an apple and its skin, the skin of the apple is about 20 times thicker relative to the apple than the atmosphere is to the size of the Earth. So this is a real fact. This is astounding to me, even considering the fact that I've studied this for so long. It still blows my mind to think that the skin of an apple is 20 times thicker compared to the apple than the atmosphere is to the Earth. And I try to highlight that with this image of the atmosphere up at the top of our slide here. So despite its modest dimensions, this thin blanket of air is nevertheless an integral part of our planet. It not only provides the air that we breathe, but also acts to protect us from the sun's dangerous ultraviolet radiation. The energy exchanges that continually occur between the atmosphere and Earth's surface and between the atmosphere and space produce the effects that we call weather and climate. Climate has a strong influence on the nature and intensity of Earth's surface processes. When climate changes, these processes respond. If, like the moon, Earth had no atmosphere, our planet would not only be lifeless, but also many of the processes and interactions that make the surface such a dynamic place could not operate. Without weathering and erosion, the face of our planet might more closely resemble that of the lunar surface, which has not changed appreciably in nearly 3 billion years. The last sphere, or second to last sphere that we will discuss, is the biosphere. The biosphere is what includes all life on Earth. Ocean life is concentrated in the sunlit surface waters of the sea. Most life on land is concentrated near the surface, with tree roots and burrowing animals reaching only a few meters underground, and then flying insects and birds reaching a few kilometers or so above Earth. A surprising variety of life forms are also adapted to extreme environments. For example, on the ocean floor, where pressures are extreme and no light penetrates. There are places where vents spew hot, mineral-rich fluids that supports communities of exotic life forms. On land, some bacteria thrive in rocks as deep as 2.5 miles and in boiling hot springs. Moreover, air currents can carry microorganisms many kilometers into the atmosphere. But even when we consider these extremes, life still must be thought of as being confined to a very narrow band near the Earth's surface. Plants and animals depend on the physical environment for the basics of life. However, organisms do more than just respond to their physical environment. Through countless interactions, life forms help maintain and alter their physical environment. Without life, the makeup and nature of the geosphere, hydrosphere, and atmosphere would be very different than they are today. Last but not least on our stop of Earth's spheres is the geosphere. Beneath the atmosphere and the ocean is the solid Earth, or what we call the geosphere. The geosphere extends from the surface to the center of the planet. By examining the most prominent surface features and their global extent, we can obtain clues to the dynamic processes that have shaped our own planet. Earth's interior, we will find, is layered, generally consisting of 3 main layers, being the core at the center, the mantle, and then the thin crust in the outer layer. As we dive into the course more, we will learn about breakups of layers. We'll talk about things called the lithosphere and asthenosphere, but we'll save that for a future time. So, now let's kind of take everything we just learned and combine it together. A system, by definition, is a group of interacting or independent parts that form a complex whole. Anyone who studies Earth will soon learn that our planet is a dynamic body with many separate but interacting parts or spheres. The hydrosphere, atmosphere, biosphere, and geosphere and all of their components can be studied separately. However, the parts are not isolated. Each is related in some way to the others to produce a complex and continuously interacting whole that we call the Earth system. A simple example of the interactions among different parts of the Earth system occurs every winter as moisture evaporates from the Pacific Ocean and subsequently falls as rain in the hills of Southern California, which can trigger destructive landslides. The processes that move water from the hydrosphere to the atmosphere and then to the solid Earth have a profound impact on the plants and animals, including humans, that inhabit the affected regions. For a second example, when a volcano erupts, lava from Earth's interior may flow out at the surface and block a nearby valley. This new obstruction influences the region's drainage system by creating a lake or causing streams to change course. The large quantities of volcanic ash and gases that can be emitted during an eruption might be blown high into the atmosphere and influence the amount of solar energy that reaches the Earth's surface in that region. The result could be a drop in air temperature over the entire hemisphere. Where the surface is covered by lava flows or thick layers of volcanic ash, existing soils are buried. This causes the soil forming processes to begin anew to transform the new surface material into soil. So, scientists have recognized that in order to more fully understand our planet, they must learn how its individual components are interconnected. So, I don't have much to say here at this moment, but I did want to include this basically map or atlas of the planet, since it kind of shows all of these systems put together. We see our land masses, which can help constitute the geosphere. We see the global ocean system, which constitutes the hydrosphere. Technically, we're looking top down, so we're looking through the atmosphere at this, and then, of course, everywhere on Earth we will find at least some varied form of life. So there's a lot of things going on in this image. You can see trenches and mid-Atlantic ridges. You can see rifts and all these different features. We'll dive into all of these in great detail at a future time. So we'll finish out this lecture with just a basic discussion on the purpose of science and what science is, including the scientific method. So in our modern society, we are constantly reminded of the benefits derived from science. But what exactly is the nature of scientific inquiry? Science is a process of investigation that leads to producing knowledge based on making careful observations and on creating explanations that make sense of those observations. All science is based on the assumption that the natural world behaves in a consistent and predictable manner that is comprehensible through careful and systematic study. The overall goal of science is to discover the underlying patterns in nature and then to use that knowledge to make predictions about what should or should not be expected given certain facts or circumstances. For example, by understanding the circumstances and processes that produce certain cloud types, meteorologists are often able to predict the approximate time and place of their formation and the intensity of the associated weather. The development of new scientific knowledge involves some basic logical processes that are universally accepted. To determine what is occurring in the natural world, scientists collect data through observations and measurement. The data collected often helps to answer well-defined questions about the natural world. Because some error is inevitable, the accuracy of a particular measurement or observation is always open to question. Nevertheless, these data are essential to scientists and serve as a springboard for the development of scientific hypotheses and theories. Once facts have been gathered and principles have been formulated to describe a natural phenomenon, investigators try to explain how or why things happened in the manner observed. They often do this by constructing a tentative or untested explanation that we call a scientific hypothesis. A spirited debate frequently ensues. As a result, extensive research is conducted by proponents of opposing hypotheses, and the results are made available to a wider scientific community in scientific journals. Before a hypothesis becomes an accepted part of scientific knowledge, it must repeatedly pass objective testing and analysis. If a hypothesis cannot be tested, it is not scientifically useful, no matter how interesting it might seem. Hypotheses must fit observations other than those used to formulate them in the first place. Hypotheses that fail rigorous testing are ultimately discarded. So, I quote, "Science is the acceptance of what works and the rejectance of what does not," or rejection of what does not. When a hypothesis has survived extensive scrutiny and when competing hypotheses have been eliminated, it may be elevated to the status of a scientific theory. The process just described, in which researchers gather facts through observation and formulate scientific hypotheses and theories, is what we call the scientific method. So, inventing hypotheses or theories to imagine how the world works and then figuring out how they can be put to the test of reality is a creative, or I guess as creative as writing poetry, composing music, or designing a skyscraper, for example. A scientific theory is a well-substantiated explanation of some aspect of the natural world. A scientific law, however, is simply an observation of the phenomenon that the theory attempts to explain. So there's a lot of, I guess, misunderstanding when we use the word theory in science. Oftentimes you'll hear somebody say, "Oh, it's just a theory," which means that it's not really validated. But, as we just discussed, a theory actually does undergo, or has undergone, significant scientific inquiry, testing, and research. So a theory is actually fairly sound when we talk about it in the scientific aspect. All right, so at this point, I have some questions. These are what I call quick check questions. So you're welcome to follow along if you are not taking this course. But if you are in my course and you're a student of mine, you do want to go through these, as this will help you prepare for some of your future exams, for example. So again, I'm going to go through each question. I'll read the question. I won't bother reading the answers. And then I'll tell you to pause the video. As you try to figure out what your answer is, you can read everything and just think, and then I will just keep the video going. So you have to pause it so that you can come up with an answer before I show it. Anyway, so the point is I give the question, you take a few seconds to think about the answer, and then continue your video and see the answer. So question number 1 for lecture 1. Which of the following is not a subset of earth science? Pause your video now and come back when you're ready. All right, so the answer is B, biology. Earth science is the name for all of the sciences that collectively seek to understand Earth and its neighbors in space. Biology is not one of the 4 that we discussed. Question number 2. Earth is blank years old. The answer is C. The Earth is 4.6 billion years old. Question number 3. A or an blank is a well-tested and widely accepted view that best explains certain scientific observations. Take a moment to pause the video and return when ready. The answer here is a theory. When a hypothesis has survived extensive scrutiny and when competing hypotheses have been eliminated, it may be elevated again to that status of being a theory. Question 4. Which of the following is not necessary for a hypothesis to be accepted by the scientific community? The answer here is C. There must be an alternate hypothesis proposed. So in other words, it is not necessary to have an alternative hypothesis to test and ultimately accept a proposed hypothesis. Question 5. The universe began about how many years ago? Now, I'm not sure if I actually brought this up yet, but at least it serves as a talking point. The universe as a whole is 13.7 billion years old, which began with the Big Bang, something we will discuss far down the road in our course. Question 6. The theory that describes the formation of the solar system is known as the what? All right, the answer here is C. It is the nebular theory. The nebular theory proposes that the bodies of our solar system evolved from an enormous rotating cloud called the solar nebula. Now, typically this would be the end of a lecture. I usually end with questions, but this is our introduction, and before I leave you with our first video, I just want to step through some mind-blowing facts. And I think I probably should have put that "how old is the universe" question at the end of this, because we will go into it here. So I'm going to leave you with just a few more slides discussing some more mind-blowing facts that kind of puts things in perspective and shows really how small we are here on Earth. So I'm just going to step through this. This is just something I put together pretty quickly. So I asked the question, where do we live? Well, obviously you might say I live at this certain address in this city or state or country. But as a whole, this is Earth science, so we live here on Earth. But where is our place in the universe? Well, we live in what we call the Milky Way galaxy, and I wanted to throw in roughly where we're located. So we're located in one of the outer bands of our Milky Way galaxy. But here's a good question. We've done a lot of observing. We've had our telescopes pointed to the sky for quite some time, and we've had amazing technological advances. So how far out have we observed stars and planets? Well, believe it or not, this circle roughly encompasses all stars and planets that we've ever observed. We have hardly even explored our own galaxy to date. So, this begs the question, if we know of so many stars, well then, if it's only in that circle, how many stars are there in our entire galaxy, right? I mean, that must be crazy. Well, as we know it today, there's at least 100 billion stars in our own galaxy. I believe there's a new estimate of 200 to 300 billion stars, actually. So at least a few 100 billion stars in our single galaxy alone. But that is just scratching the surface in terms of the universe, because how many galaxies are there in the universe? Well, here we see an image called the Hubble Ultra Deep Field. Every single image or point of light you see here is a galaxy, aside from these little pointed objects here, like you see, these are stars. But everything else you see is a galaxy, each with potentially hundreds and hundreds of billions of stars. Well, we know that there's anywhere between 100 billion to 10 trillion galaxies in the entire observable universe. So then this poses the question, well, if there's that many stars per galaxy and this many galaxies in the universe, how many stars are there in the entire universe? Well, current estimates put this at a septillion. That's a 1 followed by, I believe, 23 zeros, if I remember that correctly. So that's a pretty large number, a number that we can't even conceive to, understand as humans. So I wanted to throw in an interesting comparison. This is roughly as many grains of sand as there are on all of the world's beaches combined. So if you take a handful of sand, you couldn't even count the number of sand grains that are in your hand in any reasonable amount of time. Well, now take all sand in all of the world's beaches combined. That's roughly, give or take a lot, but roughly how many stars there are in the universe. So let's just take a look at the scale real quick. We live on Earth with roughly 7.5 billion people. Earth is a part of our solar system that includes 8 planets, not Pluto, sorry. At least not right now. Our solar system belongs to the Milky Way galaxy with about 100 billion star systems. The Milky Way belongs to what we call a galaxy cluster, and it has the specific name as the local group, which includes about 70 other galaxies. Our local group is packed together with other groups in a big cluster that we call the local supercluster. And then together, all of the structures that we find in the universe make up what we see, the entire universe, with a septillion stars. So what you see on the right here is an image of galaxies. Each dot in this image represents a galaxy. So in this image, we actually have over 1 million, which is shown in this graphic. All right, so let's take a look at the brief history of the universe. I'm just going to step through this quickly and we'll go into more depth later on. The universe began with the Big Bang some 14 billion years ago and has been expanding ever since. Within several 100,000 years, neutral hydrogen has formed. This is the first element on our periodic table. Within several billion years, matter has clumped together to start forming galaxies and clusters of galaxies. Gravity eventually drove the collapse of clouds and gas and dust to start forming stars and planets. Eventually, some stars died and in the process created heavier elements within their cores, which allowed to enrich the universe with their guts and subsequently allowed for the creation of life. So in the beginning, there was only hydrogen, a little bit of helium, and trace amounts of lithium. But as stars live out their lives, they create heavier elements, elements that we need for life. And then when those stars die, they blow up and or shed their layers and send those new materials out into the universe for other star systems to form from. And so eventually we arrive at life. So I just wanted to throw in a random image here. This is actually a picture of us. It's almost like a selfie in a sense. So this is actually an image here of Saturn. This is a real picture. And here you can see an arrow pointing to a dot. You've probably already guessed it. The reason why I'm putting this here is that dot is Earth. That's us. So I think this is just a fantastic image that helps to give a sense of scale. Okay, so at this point, I want to leave you with some videos, but I'm not going to autoplay them because of potential copyright claims and respecting those that made these videos. So in the YouTube description of this video, you're going to find several links. Please watch all of them in order, and I think it will complement this course a lot. So what you're going to find is several videos giving you some kind of perspective on the universe. It'll make you feel a little bit small. You might even have a mini existential crisis in the middle of it. But then I bring it all back together with a great video at the end, showing how important everything really is. So, as always, thank you so much for watching, and I'll see you next time. Have a good day.